And when they're separated by this much, we can deduce what kind of interactions is important between them and what's not. Now, when they're separated by like 0.1 micron to 1 micron, then we can think about, is the Coulomb interaction still important between two electrons? Well, if we had the bare Coulomb interaction, then it's still going to be important because 1 micron is a short distance, and we have the 1 over r squared, 1 over r dependence, right? But inside of a solid, we don't have the bare Coulomb interaction between two free charges. We need to take into account the charge of the lattice, and the charge of the other electrons that screens these two electrons. So what happens is that if we were to do a calculation to find the what is the Coulomb interaction between the two electrons in this screen, taking into account of the screening effect, we find that that Coulomb interaction falls off exponentially, okay? And the exponential factor, okay, so that Coulomb, the screened Coulomb interaction, okay, this is roughly the screened Coulomb interaction is something like e to the minus ks r divided by 4 pi epsilon r, and you have a e squared here. So what is this ks? This is coming from what's called the Thomson-Fermi model, and if you're interested in this, I derived this in the notes that I'll send out today. Okay. And it turns out that ks is on the order of the Fermi momentum. Okay. So it tells you that if we're about 1 over ks away from an electron, the Coulomb interaction falls off exponentially to a pretty small value, to 1/3 the original value, and at this distance is no longer important. Okay. All right. So what's important then is, of course, is what's left over, this electron interacting with the lattice, giving off a phonon, and another electron maybe absorbing this. Okay. So this interaction mediated by virtual phonon. Okay. So now let's talk about pair scattering with these relevant energy scales and length scales, and also wave vector in light. Yes.
How do they experimentally determine QE and maybe?
Oh, that's a very good question. So that will need to you will need to do some measurement based on the, well, you can first of all, let's talk about this equation. How do you get the velocity of sound? It turns out that the velocity of sound in this model is directly related to the bulk modulus, the Young modulus of the material. And so I guess if you make a measurement of that, you get this velocity of sound. And then QD, this is related to the specific heat of the material. So we can get an estimate of what's called a divide temperature, theta D, based on the specific heat of your material at that temperature. Okay. And do you guys remember what specific heat is? How much energy it absorbs before it rises 1 Kelvin? The specific heat. So specific heat is related to something called the Debye temperature, and the Debye temperature is kBT times the Debye frequency, something like that. Okay, so you have kB theta D. The Debye temperature is equal to like h bar over d. So these things come from measurements. Okay. Of course, the things like Fermi energy and the highest velocity also can come from measurement for the electrons. Okay, so let's take a 5-minute break, and then when we come back, I'll speed up a little bit and talk about the other